This is the story of a very special clock I started to build a while back. Basically, I wanted to make it a nice Christmas present, and although I thought I have plenty of time to finish it before Christmas, I ended up literally racing to get it done in time. In the end, it all came up great, and I'm very pleased with the result. I'm coreWEAVER, and here's how I built the bird clock. Designing the whole thing and then 3D modeling was what took the most time with this project. I saw a photo of a similar clock some years ago, and I wanted to design and build something like this since then. Whenever I see something I'd like to build, I try to shield myself, just like when you cover your eyes and ears to avoid any spoilers. When you hear about a new movie you'd like to see, even if I sometimes end up reinventing the wheel, I do this because I like to use my own approach and not just copy somebody else's work, do it in my own style. So I started modeling and designing all the parts. Drew a rough sketch on paper first to get my proportions and basic lines, and then I started the actual design. One thing that became clear from the get-go was that I needed to split most of the building parts into much smaller pieces, which I then print separate and then put them together to form the original part. The whole design is based on this dual shaft double stepper motor called BKA 30D R5. This thing is not very well documented. I only found some technical drawings, no electrical parameters. I didn't know what current will I need to drive the coils, and since the drawings were also not great, I bought a few of them. Then I took all the measurements myself and drew both the 3D model but also a library containing the electrical symbol and the footprint for the PCB. But in the meanwhile, before the modules arrived, I got anxious to work on the schematic, and I designed the first version of the board. That's the reason why this version has a full H bridge for each motor. But when I measured the current draw, I decided to scrap this whole section here and to drive the coils directly from the microcontroller. There are two stepper motors in this. Each one is connected to a segment of the shaft. So that means there are 4 coils, and I measured both the resistance and the current draw, which is about 15 to 20 milliamps at 5 volts, depending on what weight you'll put on the shaft. The AVR that I'm using for this project, its datasheet says that I can draw 20 milliamps on each pin on one port, and since I'm only driving one motor at a time, that should be fine. That's why I decided not to use an H bridge. That simplified this board a lot. Let's start here with a power supply. So I decided to use 2 lithium-ion batteries in series, but also I can go in with a regulated 5 volts from an external power supply. The reason for these 2 relays here is that I'm disconnecting the batteries as soon as I plug in the charger in this port, and then each battery is charged separately. When both are fully charged, this LED turns from red to green, and when I remove the charger, the relays will connect the batteries in series again. That gives me 7 point something to 8.4 volts, which goes into this switching mode regulator to make the 5 volt rail. It's a little bit oversized, this regulator here, I know. It can deliver 3 amps continuously, but initially I wanted to use bigger speakers for this clock, and I always try to oversize my power supplies whenever I can. I guess you never know when you need more power, and that bullshit with less is more doesn't go well in electronics. It's always better to have a power supply you can rely on. This here is the RTC. I thought about placing 12 LEDs, one under each hour, but I gave up to this idea, at least for this version, when I did the finishing touches on the 3D model. But these headers are here. They can be used both as inputs or outputs for the microcontroller. On the actual PCB of this clock, I did solder SMD LEDs instead of mounting the pin headers, and I used these LEDs for debugging when I wrote the firmware. There's an HC12 radio module which will be used as a receiver for remote control. I also added 5 keys for manual control. This module shares one pin with the ISP programmer, because on the Atmega 128 the TX pin of the first hardware UART is also the PDI pin. That's why I have this jumper here. Here's the audio section of the board. I used one of these MP3 TF 16p modules, wrote my own library for it. Here's the amplifier, this chip here with its circuitry. One more thing, I'm using magnets and Hall sensors to determine the position of the clock hands. And here I ran into some problems. There's a very fine balance here between multiple factors. I didn't know what magnets I'll use. They have to be strong enough for the sensors to detect their magnetic field, but not too strong, because otherwise each one will induce errors in the opposite sensor. So if they're placed too close on their radius of movement, and by the way you don't have much room to play with here, they can attract or repel each other when the minute hand comes close to the hour hand. Other problem here is their weight, because remember, you can't put too much weight on the shaft. I gave up using the H-bridge driver too, so I have to be very careful with the current draw. The geometry and the dimension of the magnet is also an important factor here, because the clock hands I designed for this clock are also pretty fragile and very thin. Basically, this was one of the biggest challenges, biggest issues I had to solve here, and it took a bit of fine-tuning and adjusting to get it right. Now, I spoke about calibration. Whenever I want to do a calibration, I rotate each hand a couple of turns. Then I start the ADC, keep rotating the hand till I detect the strongest magnetic field, and that tells me that the hand, minutes or hour, is in the exact position what I wanted it to be. So I stop the motor right there, and then I increment the position of that hand with the number of steps to correspond to the actual time, which is given by the real-time clock. And that's how the calibration works. I'm not using micro-stepping in this project. I had to count the number of steps each motor makes in a full turn, and that's 720 steps per 360 degrees. And then I did some simple math to translate everything into the way I wanted both hands to behave. The minute hand makes 12 steps each minute, and I move the hour hand also 12 steps every 12 minutes. Each time the minute goes from 59 to 0 and the hour changes, I play an audio file containing a bird song. There are different sound volumes for night and day. I can set the time both manually or remotely. I can read the battery status or completely turn off the volume. The nice thing about this hardware is it doesn't have to be a bird clock. I can put like ocean sounds or animated cartoon characters. I'm sure you get the idea. So it's pretty easy to modify this, and I designed it in such a way so I can easily open it both from the front side if I want to access this background here and the hands, but also from the back side, which gives me access to the PCB if I want to change the batteries, or let's say if I want to modify the firmware. So I'm going to let you guys sit back and enjoy first the soldering part, and then the manufacturing of the case and the assembly. Finally, we've reached the end of this project, and it has been an amazing ride. I always get a little sentimental when I finish a project like this, and it's like a unique journey coming to an end. I'm so proud of this. I think it looks awesome, and I really do hope she's gonna like it too, because this is gonna be a Christmas present, a special one. I also built this very simple remote control for this clock. It's only temporary because I didn't have much time. It's just a microcontroller and some keys. The clock has its own buttons here for a few basic commands, but I still wanted to have this remote control too. Ultimately, this clock is going to be hanging on a wall, and it's going to be a lot easier to control it like this than pressing these buttons. I barely managed to finish it in time and just need to do one more thing. I need to charge the batteries because they're drained after this video. But for now, I'm just gonna enjoy this moment and see how it works. So as soon as I'm gonna flip this power switch, it's gonna go through the calibration sequence and it will adjust itself to the internal RTC. Calibration sequence initiated. Calibration complete.
Es ist 14 Uhr. Es ist 11 Uhr. Es ist 9 Uhr.
Calibration sequence initiated. If you want to see more projects like this, make sure to smash that like button and subscribe to this channel if you haven't already. Now would be a great time to do this, and for all of you out there who waited so long for another project, I just want to thank you for your patience and your support. I went through the most difficult times of my life lately, and it means a whole lot more than I can say to have you near me. I love you guys, and I'll see you soon with the next project. This is coreWEAVER signing off.